All right, everyone. So in this video, we're going to be discussing average, atomic mass, and abundance. So remember, in our last video, we were talking about isotopes and how isotopes are atoms of the same element that have the same protons, which is what makes them the same element, but they have different neutrons. So for example, if I look at carbon-13, carbon-12, and carbon-14, we know that they're all carbon, which means that they all have 6 protons. But because their mass numbers are different, they must have a different number of neutrons. We have 6 neutrons here, 7 neutrons, and 8 neutrons added to the 6 protons to get their mass number. But not all of these isotopes of carbon, carbon-14, 13, and 12, are as common or abundant in the world. And so we're going to be talking about abundance. So with natural abundance, okay, this is how common or rare, depending on the thing, whatever it is you're talking about, it's how common or rare something is in the world. Okay, so we know that there are some things that are extremely common and other things that are more rare, and that is its natural abundance. Now, an average atomic mass is a weighted average of the isotopes, of the mass of the isotopes of an element, and it's based on the abundance. So because not all of them are as common as others, they do not all have the same contribution to the average. For example, it'd be like if you're calculating your grade in chemistry, right? Let's say there are only 2 categories. You have quizzes and you have tests. Well, we know that tests are worth more. So let's say quizzes were 30% and your tests were worth 70% of your overall grade, right? And so we know those would be added up together to get your final grade in the class. Well, it'd be 30 and 70 if you got a 100 on everything. But let's say you get a 90% on most of your quizzes, but you get 40s on most of your tests. What is your final grade going to be closer to, the 90 or the 40? And if you were to do that math, it would be closer to the 40. Why? Because the test category is worth more. It's a higher percentage. And so with abundance, we can skip this part about the dessert. But if you look at the pie chart over here, we know that something is more abundant when it takes up the most space, okay, or it has the biggest percentage. And so when we talk about abundance, it means the ratio of one item to the total amount. Okay, so if we were looking at these desserts, okay, it would be the ratio of jelly beans to all of them combined. And so an isotope abundance is the ratio of one isotope of an element compared to the total number of atoms. So whenever you're trying to find a percentage, you want to make sure that you know actually how to calculate a percentage. So anytime you're trying to do that, okay, a percentage is always equal to the part you're looking for divided by the total amount times 100. Okay, so for example, if I wanted to know how many girls were in the class, right, I would count the total number of people. So let's say there are 30 students or 30 people in the classroom, and 15 of them identify as girls, right? 15 divided by 30 times 100 would give us a 50%, okay? And so you always do that. And so this is how you would figure out your percent abundance of isotopes. It would be the number of a particular element, or the number of a particular isotope, the total number of atoms for that element, and then multiply it by 100. And so for here, okay, if we look at our isotopes, okay, we're going to look at chlorine. Chlorine exists naturally as two isotopes, chlorine-35 and chlorine-37. So when we're looking at protons, neutrons, and electrons, okay, I would like you to pause the video, answer this question, and then resume when you're ready to check your work. Okay, so you should know that chlorine, both of them will have 17 protons and 17 electrons because we assume it's neutral. But chlorine-35 will also have 17 neutrons, but chlorine-37 will have 19 neutrons. And so we get that by the mass number minus our protons gives us our neutrons. And so when we look at the average atomic mass of chlorine from the periodic table, remember you can find that by looking at chlorine's box, so it's number 17, and its average atomic mass is at the bottom, right here, 35.45. So the average atomic mass is 35.45 atomic mass units. And when we think about which one is most abundant, we can think back to our analogy about the grade, okay? Whichever, if our final grade was closer to 40%, so let's say it was a 50%, this is much closer to 40, which was the test category, right? And what that tells you is that it must have had the highest percentage. So whichever isotope, either chlorine-35 or chlorine-37, is the closest to our average atomic mass, that's going to be the one that's the most common. So we can say that chlorine-35 is the most abundant because it is closest to the mass, to the average mass on the periodic table. And that's how we identify which one is the most abundant when just looking at our periodic table. But how do we actually calculate that number? Okay, so average atomic mass has a formula. Okay, so you always take the percent abundance, multiply it by your mass number, and you do that for every isotope. So you would add that to the next one, your percent abundance times your mass number, and you would literally just keep adding that setup for every isotope. So if this was for isotope number 1 and this was for isotope number 2, okay, and then at the very end you divide by 100. Now, one thing to keep in mind, do not, okay, I repeat, do not put the percent sign in your calculator. If you do, you're going to mess everything completely up and you're going to get the wrong answer. And unfortunately for you, in a multiple choice question, that wrong answer will probably be one of the options. And you'll be like, yay, I got the answer right. It's right there. It's, I don't know, A. And you'll be like, no, still wrong. Okay, so let's look at this example. So it says one chlorine isotope with 18 neutrons has an abundance of 75.77% and a mass number of 35 AMU. The other chlorine isotope has 20 neutrons and an abundance of 24.23% and a mass number of 37 AMU. What is the average atomic mass? So if we do this, we take our first isotope, which I highlighted in green, and our percent abundance, so 75.77 times 35 AMU, plus our second one, so 24.23% times 37 AMU, and we'll divide it all by 100 at the end. Now, if you're using a regular calculator, you can do this all in one step in your calculator. Just make sure you use your parentheses. If you're doing it at home, just on your cell phone calculator, it's not recommended, but it can be done. I just recommend that you practice using the calculator you plan on using during a quiz or test. When you put it in your calculator, you should get an answer of 35.48 0.46 in your calculator. But we should be rounding it to have two numbers after the decimal. So the answer would be 35.48 atomic mass units, which you notice is very, very close to what is actually on the periodic table. Their percentages and or mass numbers might be a little more precise than the ones we used in this problem. And on the next page, you just have some practice problems here. I will put the answers in this video. So pause the video, practice, and then I will pop the answers up onto the screen. So pause, do the practice, and then press play when you're ready to check your work. Okay, so for A, B, C, and D, you can check your work, or well, you can check your answer. If you got something different, you want to make sure that you put it in your calculator correctly. And if you're still not able to get this answer, you can come talk to me about it in class. For this word problem here, they wanted to know which isotope is the most abundant. So you have to compare the mass of each isotope to the average atomic mass, which is highlighted in yellow. And you should note that gallium-39 is closer, or excuse me, gallium-69 is closer to the average atomic mass. Therefore, it must be the most abundant and have the highest percentage, because you'll notice that for each of these, our answer is the closest to the mass that had the highest percentage. So the one with the highest percentage had the mass closest to it. And so that is going to be a common factor every single time. Now, for this last question, I wanted to go through this actually in a video, not just to check your answers, because it's a little bit different and it is a multiple choice question, and some of you have been struggling with thinking through all of your questions. So it wants to know which student correctly calculated the correct average atomic mass and why. And so you're going to have different masses and different students, and so in order to do this, we're actually going to have to do it ourselves. So they tell you that a sample of lithium consists of 400 atoms. So we have a section of 400 total atoms, right? And they say that 30 atoms are the lithium-6 isotope, and 370 of the atoms are going to be the lithium-7 isotope. So we know that lithium-7 is more abundant, but in order to calculate this, we actually need our percentage. So we're going to have to calculate our percentage on our own. So 370 divided by 400 times 100 is how we would actually get our percent abundance for lithium-7, which is 92.5%. So it's 92.5% lithium-7. And then we know that 30 divided by 400 times 100, which is what we will do for lithium-6, tells us that we have 7.5% lithium-6. And both of our percentages add up to equal 100, so we know that we haven't made a mistake. So knowing this, we can actually calculate our percentage, or our average atomic mass. So we can say that 92.5% times, and so they give us a very specific mass for lithium, so we want to use that one. So 92.5% times 7.016 AMU plus our 7.5% times 6.015 AMU, all divided by 100. And so remember, when you're doing this in your calculator, you do not want to put the percent sign in your calculator, because otherwise it will get messed up. That's why we're doing the divide by 100 part. And so when you actually do this in your calculator, you should get a number that's 6.94 AMU. And so that's great, but we need to look at our answers. So let's see who had it. So student 1 calculated the average atomic mass as 6.94. That matches what we had. And so you can look at the way they did it as well. It's the only one that matches ours. Others got close. But one thing you notice is if you look at how they calculated it, it says student 1 determined the percent abundance for each isotope, which we did, and then multiplied the percent abundance by the average atomic mass of its isotope and took the sum. Basically added them together. That's what we did. It said student 2 did it by the average mass of the two isotopes. So they just added them divided by 2. That's not correct because we know this is a weighted average. And student 3 said that she added the isotopes and then multiplied by the ratio. That's, again, not how it works because it's not just multiplying by the ratio. Each mass has to be multiplied individually. And then number 4, it said they just added the mass of the two isotopes. That's not how it works. So for our answer, student 1 is definitely correct. Okay. And we can see that based on the math that we got. In theory, if you knew average atomic mass calculations well enough, you wouldn't have needed to do this math if you could look and realize that student 1 describes doing the math correctly, whereas all of these other students do not describe the correct procedure for doing the math. So hopefully you feel good about your practice because there will definitely be a quiz next week.